Today, let's solve a classic bioprocess engineering problem involving a chemostat and Monod Kinetics. This is a very common type of question in GATE and other biotech exams. So let's break it down. First, let's look at what the question gives us. We have a 2-liter bioreactor. It's operating at a flow rate of 0.8 liters per hour. So the F will be 0.8 liters per hour. And we have a sterile feed with a substrate concentration of 10 grams per liter. 10 grams per liter of the substrate. This is our S naught substrate S naught, let it be, that is given as 10 grams per liter. Next we have the kinetic parameters. The maximum specific growth rate, that is maximum specific growth rate is given as 0.6 per hour. So we can write it as mu max will be 0.6 per hour. The Monod constant Ks is 0.5 grams per liter. Monod constant is 0.5 grams per liter. So Ks is 0.5 grams per liter. And we have given a biomass yield coefficient as 0.4. That is y of x bar s will be 0.4 grams per grams. Next, now let us start with the step 1. That is the dilution rate. The question asks us to find the exit biomass concentration. So to get there, we first need to find the dilution rate. That is, D is the dilution rate. We know that dilution rate is simply flow rate divided by the volume. Flow rate divided by the volume. So that's 0.8 divided by 2. So the flow rate is given as 0.8, volume is 2, this is liters, this is liter per hour. So the dilution rate we have got now is 0.4, it cancelled, so it is per hour. Now let us come to step 2. Step 2 is substrate concentration. So in substrate concentration, let us call it S. Here is the key concept. Since this is a chemostat operating at a steady state, the specific growth rate mu is equal to the dilution rate D. Why? Because it is a steady state. Because it is a steady state. Using the Monod equation, we can write D will be mu max into S divided by Ks plus S. Let's substitute our values. We know D is 0.4 and mu max is 0.6. And yes, we don't know yes, so let us write it as it is. Now we need to find yes the residual substrate concentration. We have Ks. Ks is given as 0.5 plus yes. So we write so let us simply substitute everything, and now we get is, bring the yes terms to one side, we get 0.2. So yes equals to 1 gram per liter. Yes will be equal to 1 gram per liter because these both will get cancelled. Okay. Now let us come to step 3. In step 3, we got to calculate the biomass concentration. Biomass concentration, and let us conclude it here. We are almost there. The question asks for the exit biomass concentration. So we use the yield equation for this. Biomass produced equals the yield coefficient times the substrate consumed. Remember, substrate consumed is feed minus exit. We have x is equal to y of x bar s into substrate in the input minus substrate in the output. So we have x is equal to 0.4 10 minus 1, which is nothing but x is equal to 3.6 grams per liter. So this is the final answer. So the exit biomass concentration is 3.6 grams per liter.